Until now we have discussed about the different digital to analog conversion techniques, binary weighted resistors method, R2 to R ladder resistor method. Now we are discussing about analog to digital conversion technique. Here we are using the counter mainly. That's why this is also called as counter method. The heart of this technique is the counter. Here you can observe this is a control logic in this block diagram. When we give the start command to this, then this control logic resets the counter and it enables the clock signal generator. Because the control logic resets the counter value starts from 0. This clock signal generator generates a pulse. Each time when it's sending the pulse, the counter value changes from 0 to 1, 1 to 2, 2 to 3, 3 to 4, like that it is changing. Now this counter value, the binary equivalent value, this is MSB and this is LSB. This binary value is generated here. Directly we can display, but we do not know whether that is the analog, means the digital value is equivalent of the analog or not, we do not know. So we are asking to the DAC. The DAC can be either it is R2 to R ladder network DAC or it is binary weighted resistors DAC. So this DAC converts this binary value. Example, if it is 1, it converts, and then R2, example 1, 0, then it converts to analog value 2. Now it sends here, example 2. But really the analog value is 8, example assume. Because this 2 is less than 8, still the comparator value is high and the control logic, because we are supplying high, this process will be continued. Now one more clock pulse will be sent. Now the counter value increases to 3. Binary equivalent value is 1, 1. Again this binary value will be converted to analog 3. It checks whether 3 is greater than 8 or not. No. Still the comparator value is 1. Again it generates a clock pulse. Now its value increments to 4. Because it is for 1, 0, 0. Now its value we are converting to analog. Its value is 4. Again we are checking whether this 4 is greater than 8 or not. No. Again the clock pulse will be sent. Like that its value will be incremented 5, 6, 7. Now its value is 7. 7 means 1, 1, 1. Now it is converting the digital value to analog. Its value is 7. This is 7, it is checking. Again its value is 1. Now the clock pulse will be sent. The counter will be incremented to 8. So here 1, 0, 0, 0. So the counter value is 1, 0, 0, 0. Now it will convert to analog. Its value is 8. And it is 8. Because both values are equal, automatically it will be switched to 0. Because it is 0, the control logic immediately disables the clock signal generator. Hey, clock signal generator, stop. Do not send any more clock pulse. At that time the counter displays the value. What is the counter value at that time? 1, 0, 0, 0. So whatever the value is being displayed on the counter, that is the digital equivalent of the whatever the input we have given. What is the input we have given? Analog value 8 volts. What is its digital value? 1, 0, 0, 0. Because it is working step by step, for 8 it is taking how many steps? 8 steps it is taking. How many clock pulses we require? 8 clock pulses. 8 clock pulses we require. Similarly, the disadvantage with the counter method is it works very slowly because it works with the step-by-step procedure. That is the disadvantage with this. But the operation is working in a loop, iterative manner. It is very simple in construction, that is the advantage. But the disadvantage is it takes more amount of time to generate the digital value. Again, we are explaining the operation. Initially, when we are giving the start command, we are expecting, our input we have given here, 8. We are expecting this counter to display equivalent digital value. When we are giving the start command, this control logic disables the counter, resets the counter. We should not use the word disable. It resets the counter. Then the counter value will be 0. And it enables the clock signal generator. When it enables the clock signal generator, it sends one pulse. Each time the clock signal generator is sending a pulse, the counter value increases. Now the counter value is 0, 1. 0, 1, the binary equivalent value that will be converted to analog value, that value will be 1. We are checking whether that value is greater than the input we have supplied at the non-inverting terminal of this comparator or not. Until the value is not equal or until the value do not cross the input we have given at the non-inverting terminal, the comparator output will be 1. When the value equals the non-inverting terminal input value, then the comparator value becomes 0 and it disables the clock signal generator. Immediately the counter will display the value. This is how analog to digital conversion will be done by using the counter method.